Hello everyone and welcome back to Geotech Masters. I'm thrilled to start a brand new journey with you today. We are beginning our comprehensive series on rock classification. We'll be using the international standard ISO 14689 as our guide. This series is the direct sequel to our previous course on soil classification. Now we are ready to dig deeper and explore the hard materials beneath the Earth's surface. In this first episode, we'll set the foundation for the entire course. We need to understand exactly what this standard covers. It is not just about naming stones. It is about understanding the rules for identifying and describing rock for engineering purposes. We will look at the scope of the standard to see where it applies in our daily work. Most importantly, we will define the tricky boundary between soil and rock. We will also learn the essential vocabulary that every geotechnical engineer must know. By the end of this video, you will understand the difference between rock material and rock mass. These are critical concepts for your career. So, let's get started.
Before we dive into the details, we want to ask you a few questions. Have you ever wondered when a hard soil officially becomes a weak rock? Is there a specific line where one ends and the other begins? This is a common challenge we face in the field. Also, think about drilling logs. When the drill rig stops advancing, we call it refusal. But does drilling refusal always mean we have hit bedrock, or could it be something else? We will uncover the truth behind this common assumption today. Finally, what is the difference between a piece of rock in your hand and the rock slope you see on a highway? One is a sample and the other is a system. We call this the rock mass. Why is this distinction so vital for safety? Stick around because we are going to answer all of these questions in this video. Let's look at the scope of ISO 14689. This document specifies the rules for the identification and description of rock. It covers both the rock material and the rock mass. This is the global standard we use to make sure we are all speaking the same language. This standard applies specifically to geotechnics and civil engineering. It is used for descriptions on cores, other samples of rock, and even exposures of rock masses in the field. Whether you are building a tunnel or a foundation, this standard provides the rules you must follow. The identification is based on several factors. We look at mineralogical composition, genetic aspects, structure, grain size, and discontinuities. It provides a system to describe these features accurately. However, please note that rock mass classification systems for design, like RMR or Q system, are outside the scope of this specific document, though we will touch on them later in the course. Now, we must address a very important concept, the boundary between soil and rock. If you have taken our previous course, the Geotechnical Engineer's Guide to Soil Classification, you are already an expert on soil classification. That course covers soils. But where does that standard classification stop and this one begin? In geotechnical engineering, the line is not always clear geologically. We need a practical definition. We need to know which standard to use when we are logging a borehole. Using the wrong standard can lead to incorrect design assumptions. Here is the simple rule provided by the standards. Rock is a material that cannot be disaggregated by hand in water. If you put a lump of material in water and you can break it apart into individual grains with your fingers, it is soil. If it stays solid and requires a hammer to break, we classify it as rock. This is the practical test we use to switch from the soil standard to the rock standard. Let's talk about a common mistake in the field. We call it the refusal myth. Many engineers assume that when the standard penetration test, or SPT, hits 50 blows for very little penetration, they have hit rock. We call this refusal. However, refusal is an action, not a material description. Very dense soil can cause refusal. A large cobble or boulder suspended in a soil layer can cause refusal. If you simply write rock on the log because the drill stopped, you might be wrong. It is essential to recover a sample to prove it is rock. You must look at the sample. Is it a continuous core of bedrock, or is it a piece of gravel? Remember, the standard requires us to identify the material based on its composition and structure, not just how hard it is to drill.
Now, let's look at the official terms and definitions from the standard. First, we have rock. In this context, we often call it intact rock or rock material. Rock is a naturally occurring assemblage. It is an aggregate of mineral grains, crystals, or mineral-based particles. These particles are compacted, cemented, or otherwise bound together. This binding is what gives rock its strength. The key definition is that it cannot be disaggregated by hand in water. This separates it from soil. Rock materials are generally of greater strength than soils. When we describe rock material, we are looking at the small piece we hold in our hand, ignoring the large cracks in the ground.
Next, we have the rock mass. This is a very important distinction. The rock mass is the rock material together with the discontinuities and weathering zones. It is the big picture. Imagine a brick wall. The brick itself is the rock material. The wall, with all the bricks and the mortar joints between them, is the rock mass. In nature, the rock mass includes all the fractures, joints, and faults. For engineering, the rock mass is usually more important than the rock material. A tunnel or a slope usually fails along the cracks, not through the solid rock. Therefore, the standard requires us to describe the rock mass structure, not just the small samples we bring to the lab. We mentioned discontinuities, so let's define them. A discontinuity is a break in the rock material continuity. It is a plane of weakness. These are the weak links in the geotechnical system. A discontinuity can be open or it can be closed. It includes joints, bedding planes, faults, and shears. In the standard, it is defined as a break that is open or can open under stress. When we perform site investigations, identifying these breaks is critical. If we only test the solid core, we miss the most critical part of the ground's behavior. We must measure their spacing, orientation, and condition. We will cover how to measure these in detail in later episodes. The standard also defines terms regarding the internal structure of the rock material. We look at fabric and texture. Fabric refers to the preferred orientation or spatial arrangement of the grains and crystals. For example, in sedimentary rocks, the fabric might show the layers where the sediment was deposited. In metamorphic rocks, it might show how the minerals were squeezed and aligned. We also look for texture. This describes the size, shape, and arrangement of the grains. Is it fine-grained or coarse-grained? These details help us name the rock correctly, which we will discuss in the next video on rock identification. Why do we spend time on these definitions? It is all about communication. When you write rock mass in a report, the design engineer needs to know exactly what you mean. Misunderstanding these terms can lead to expensive mistakes. If you design a foundation based on the strength of the rock material, but the rock mass is full of open joints, the foundation might fail. Using standard definitions provides legal and contractual clarity. If there's a dispute about the ground conditions, we go back to these definitions. Following the standard terms protects you and your client. The standard also guides us on how to identify rock types based on their genetic group. We have three main groups. First are sedimentary rocks, which can be clastic, chemical, or organic. Second are igneous rocks. These are formed from molten rock and can be plutonic or volcanic. Third are metamorphic rocks. These have been changed by heat and pressure. The standard also mentions duricrusts, which are cemented zones in weathered rock or soil. We will go into detail on how to name these rocks in the next episode. Let's summarize what we have learned today. ISO 14689 provides the rules for identifying and describing rock for civil engineering. It applies to cores, samples, and field exposures. We learn the critical difference between rock material, which is the intact block, and rock mass, which includes the discontinuities. We also clarified the boundary between soil and rock based on whether it breaks down in water. Using these standardized terms is essential. It ensures that our data is accurate, reliable, and understood by engineers around the world. This foundation will help us as we move into the practical steps of describing rock in the next videos. Now, we have a question for you. In your experience, have you ever encountered a situation where drilling refusal was mistaken for bedrock, but it turned out to be a boulder? How did that affect the project? Please share your stories in the comments section. I would love to hear from you. Also, if you have a friend or colleague who is working in site investigation, please introduce this course to them. It might be very helpful for their work. Don't forget that you have access to the full course contents. This includes not only these presentation slides, but also a helpful mind map of this topic. This mind map is a great way to learn quickly and have a handy note for the field. These are also some references that we have used to prepare this course. Thank you for watching, and we will see you in the next episode, where we will learn how to name rocks in the field.